Okay, we're waiting on that to go live. Amazing. Cool. So, in the audio application that we've been working on, I'm gonna wait for people to get online first, and then I'll start. Cool. So let's look at this. In the audio application that we've been working on in the past few days, I don't know. I'm not so sure. But however, in the application that we've been working on in the past few episodes, we've been trying to build a system that can sense audio signals. And then we put a BLE network on this and and such and so on and so forth. And if you're here for the last stream, you know that the audio part is giving us an issue. This is custom. This is for custom. So yeah, the audio recording, the periodic audio recording, which is when I want to do some audio sensing, basically sense some audio and just be like, oh, I sense this audio signals, and then I stop, and then this part is being an issue. And the reason it's being an issue is because I think I don't know how to use the ITOS libraries, and I don't know how to use the MEMSLab libraries. So between the both of those, there's some rudimentary error that I am making that is preventing me from shipping periodic audio recognition. And then after that, we'll advance. Once we can, not audio recognition, audio sensing, just know that audio is happening. Once we can sense that periodically over and over again, we can start doing something with the audio that we sense. But the first thing we need to fix is to be able to collect the data. However, that's gotten boring. It's been a few episodes of that, and I think I'm going to take a break on that and let my brain defragment so that we can do something else. What I wanted to do today is to if we're going to be building an embedded application that is capable of recognizing sounds, one of the best things we can do is understand how sound is recognized and how computers recognize things. And basically if you start down that path, you end up doing this thing where you want to implement things called neural networks and machine learning, and after 10 years you get to something like AI, artificial intelligence and such, and that's like building up on stuff. So we're not there yet. And this is not like the next greatest and best of anything. We're just doing stuff to see how it works and to make sure we understand that it works really well, and also to build our intuition on how these things work. Okay. Additionally to that, I was speaking to a friend yesterday, and they showed me this. I really hope I can show it. IMX. I think it's public. IMX 500. Yeah. So I hope this is public. So Sony is releasing an IMX 500 IMX 500 chip. Yeah, this should be public. So Sony is releasing an IMX 500 chip, which is a camera, which is a vision sensor that has a neural network on board. And you can use this neural network to do stuff. However, the thing about neural networks is, before you know what neural networks are, you can't really use them. Okay? So we want to kind of build up, excuse me. Pardon me. So we want to build up our intuition or our understanding of neural networks and how to use them and how these things work, so that we can kind of be able to move between things and do things that are, sufficiently complicated. You don't have to build your own neural networks to use them. You can use there's so many options, especially the day I'm making this, in the year I'm making this. You can use, there's so many libraries that can build neural networks, and you can go straight to using them now. However, if the point was to use a library, then this is not the video for it. The point here is to understand what is happening in the background, how it's happening, and to be able to have innate intuitive understanding that this is what happens. And then once you have that understanding, it's very easy to build up on things upwards. We can build up on other things and see what is happening, and go on and so on and so forth. So the exercise that we're going to be embarking on today is implementing two types of neurons, or rather artificial neurons. Okay, and the reason we can't implement real neurons, because those happen in biological brains, and you can't clone stuff. I think you can clone stuff, but you're not allowed to clone stuff. I don't know. Anyways, just big biology problems. So what we're going to do today is we're going to go through what neurons are, try and understand them. And then once we understand them, we're going to try and implement two simple types of neurons. Okay, two simple types of artificial neurons. However, this is the thing about neurons. At the end of the day, all of this is sort of like algebra, or just basic math with one small function. If you build up on it, if you build up on that function, you can end up building quite a complicated system. And that's the same thing with computers. If you have a bunch of gates, if you have an and, an or, and a nor, especially if you have an and, an or, and a nor, you can end up building a NAND, which is a not and a and. Well, you need a not. You can end up building a NAT, which is a NAND, which is a not and an and. And if you have a not and an and, these are gates I'm talking about. If you have this logic gates, a not and an and, you can end up building any computational unit you need. So a NAND is what you basically need to build any sort of computational need. And a NAND is a function, or a gate that takes two inputs and produces one output. In a NAND, it will be not and. So a NAND will produce outputs will produce a true output if both inputs are nots. So if both inputs are 0, 0, it will produce a 1 output. If both inputs are if it's and, so if it's 1 and 1, it will produce a 1. So 1 and 1 produce a 1, 0 and 0 produce a 1, 0 and 1 no, 0 1, 1 0 no. Okay, or a faulty thing. But that's a different problem. That's how to build up computational stuff. But so let's look at what neurons are, and sort of how they move from programming to from biology to programming, and then we'll implement a couple of them. So let's say in our application now that we have been considering now, the audio sensing application. And this audio sensing application, if we wanted to recognize a sound, let's make a distinct sound. Let's say we wanted to recognize a sound of glass breaking. Okay. The moment you start implementing such a function, it grows so quickly, so big. It grows very complicated very quickly, because you're doing basically, if there's a sound and the sound is like this, but it's not like that, and it's not like that as well, because there's a lot of sounds that sound the same as breaking glass, but they're not the same. So you have to narrow down completely to the specification of how glass breaking. What happens here is you'll make a function that quickly becomes riddled with branches, and it quickly becomes riddled with exceptions. So this is not a glass, this is not a glass, this is not a glass, and then you'll end up with this huge function that does one very simple thing, and then most of the time it won't be stable, because what if the lab that you were using was quiet and then you went outside and then there was more noise in the signal plus the glass breaking, and your function doesn't know how to handle the sound and all of this and such. Now, this it almost sounds counterintuitive, because isn't it just easy? Can't you just hear something and recognize it? It's when you start realizing how your body does this that you realize that it's not that it's an easy thing to recognize sound, rather it's quite difficult, and your brain is a supercomputer that has been made over thousands and thousands of years, and it's basically been taught, it's learned how to do this. So it's not that recognizing the sound of breaking glass is easy, it's that your brain is very, very, very good, very, 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 very good at recognizing this sound. And the way your brain does this is by something called we have many of them. We have many cortexes, and my understanding kind of points me to say that a cortex is a neural network, but I might be wrong. But either way, a cortex could be either a neural network or a layer in a neural network. But a layer in a neural network is still a neural network, because that's still neurons, and they could connect to the sides. And based on whether they're connecting to the next layer or to their layer, the neural network could be convoluted or could be a relative. It could be many kinds of neural networks. So based on their connections. So let's look at. Let me just pull up something from my reference document. Let's look at something here. So by the way, this book, Neural Networks and Deep Learning, this is a really good book, and it's free. You can use it, and if you feel like you like it, there's you could end up you could donate to it and such. Let me look for where this was explained properly, because I'm holding quite a bit. Convolute. 2, 3. So let's see. But there's basically, based on how the neurons are connected in the network, based on how they're connected, it becomes a different type of network. I'm not going to belabor this stream with that. Let's just keep on the simple path so that we can understand what we're doing. And basically, our brain has something called an auditory cortex, and an auditory cortex is a neural network that basically is layered of many layers of neurons, and these neurons will basically abstract information the deeper into the layers you go. So the first neurons will do some very basic thing, and then based on that they will feed their output into a second layer of neurons that will also do some understanding based on their inputs, and then they will feed their output into more and more neurons. And what ends up happening is something to the sort of this diagram. So you have some inputs, and then those inputs go into some neurons, and then those neurons produce some outputs, and those outputs go into some other neurons, and then the second layer, they do some computation, and then after some n number of layers you get an output. Okay, a final output, not an output that's going to another neuron. Although when you're doing computing, you want to hold small bits of information in the place, so when you're just doing outputs, you don't care whether it's going to another neuron or it's going to a final output. Someone else, like, The layer above should decide that. You just do what you need to do. But basically, that's what's happening. You have inputs coming into a neuron, and then neurons feeding other neurons, and that, and that, and that, and that. And basically, that is what a neural network is. And that is also sort of what our brain is doing when it's recognizing audio. Because you have the first layer, it gets some basic signals, it recognizes into something, it computes them into an abstracted thing, and then it feeds this into a higher and higher and higher and higher and higher layer, and then at some point you've made such an abstracted decision that you've just said something like check glass, and if it was glass breaking, boom, you know it was glass breaking. If it wasn't glass breaking, boom, you know it wasn't glass breaking. But in reality, that's not how it happens. It goes step by step by step by step by step. This is how your brain does it. Okay? So I'm going to pose for either questions or why do people use sigmoid neurons if rel U is more stable? Well, we'll see why. Let's look at, you're asking about rel U. Rel U neurons. Rel U neurons. So rectifier neural networks. So this. I think it's because of the. I really think it's because of the characteristics of the step function in rel U. But it looks like it has the same step function over here. This looks like a sigmoid neuron here. The produces one output. So this this is not exactly a sigmoid neuron. There's a bunch of missing factors here. But that for another day. You know, let's just first build the basic intuitiveness of what we're doing before we start like debating and such. Because let's build context first. I have a feeling it's because Abhishek. I have a feeling it's because of the shape of the function, the shape of the step curve, or the shape of the step function, or the curvature of the thing. And basically, it's almost like going from a probability density function to a probability mass function. You don't want that sharpness. You want that gradualness, and then you want to be able to widen it and narrow it. It's Gaussian again. It's Gaussian statistics again. You want to be able to do that narrowing and expanding quite easily, and basically adjusting precision versus accuracy. And this is here. DSP for engineers. DSP scientific guide for DSP for engineers. So there's a difference between accuracy and where's the chapters? Where can I read this book? Show me the book. Yeah. So there's a difference between precision and accuracy. And precision is let's see. So precision. Okay. So I want to see. Okay. When deciding, okay, cool. I'll plus so that everyone can see. When deciding which name to call the problem, ask yourself two questions. First, will averaging successive readings provide a better measurement? If yes, the error is precision. If no, call it accuracy. So there's a difference between precision and accuracy. And precision is basically, here it shows. Precision is basically how close you are to the true value, how close your mean is to the true value, and then the accuracy is how wide of a Gaussian thing you have, or how wide of a function you have, or of a what do you call it? Of a plotting you have that covers the thing. But anyways, that's a digression. We're learning. We're just learning. We're discovering this stuff. So, what we really want to do is we want to basically build a basic neuron so that we can understand what a neuron is, and then we can build up on that. We'll do several streams. We'll do as many as it takes to be able to build a neural network. And we'll try and do all of this in C. Touch wood. We'll try and do all of this in C. Excuse me. Okay. Cool. So, let's go back. Where was I before I answered that question? I think we were introducing. I think we were just talked about the auditory cortex and how it works. So there's layers of neurons, and these neurons are computing inputs and feeding other layers out. We'll get to these layers and what they're called and how they work together later. So right now, let's go down, all the way down to just one single neuron, as is always in computing. Let's start with one thing, make one thing work, and then we can go forward. And we've introduced where this would be a problem, where this would be applicable. So let's start now actually doing something. So let's consider working towards implementation and see what happens. Okay. So there's been work since the last century, well, the 1940s, the 1900s. This is so scary to say this. This is 60 years ago. This is half. So there's been work since the 1940s, and this work has basically been building up on how to making the mathematical formula of how to recognize, or rather how to make decisions. And around the 1950s, a formula was made, and this formula was called the perceptron neuron. And what a perceptron neuron is it's our replication of what a neuron is in the human body. Let's look at what a neuron is in biology. So let's control plus. So let's zoom that. So let's say a neuron or a nerve cell is an excitable cell that fires electrical signal, goes on or off. You see? A neuron is a GPIO. There you go. We've done it. One. We're done. We finished this. So, a neuron is an excitable cell that fires electrical signals called action potentials across a neural network in the nervous system. So your nervous system, your human nervous system, is a neural network. Should I Google it so we see it? Do I want this page? Human nervous system. So this is a neural network that is in your body. Images, please show me. Please show me an image. This is a neural network that's in your body. And it's made of billions and hundreds of billions of neurons. And each of these neurons are feeding other neurons, or being fed from other neurons. Of course, there's neurons at the skin, that are being fed from actual inputs. And then there's neurons at the brain that are being fed like abstracted information all the way there, and it can just snap a decision, okay? So, okay. The more I think about it, the more I realize biologists sort of make the best computer scientists, because biologists are basically studying one of the best supercomputers, and then computer scientists are going like, oh, we're good at this, we're gonna make one. And then it's like, she can't really make what nature's made over the last 100 million years or something, or 13 billion years or whatever, since life. When did life start? 4 billion years ago. How old is life? How old is life on Earth? Let's look at it. How old is life on Earth? So we've been here for like, I think, a quarter, 20% of the 4 billion. Earth was formed history of life on Earth. The history of life on Earth traces to the processes by which living and extinct organisms evolved from the earliest emergence of life to the present day. Earth formed about 4.5 billion years ago. So the universe was existent for like 9 billion years. the universe was around for 9 billion years before Earth was formed. And then I think life has only existed for like 20% of the 4 billion. Earth formed 4 billion years ago. And then the earliest evidence of life comes from the biogen carbon signatures and stromatolite fossils discovered in 3.7 billion year old. Wait, that's actually pretty fast. It's in the universe. Life on Earth was quite quick, but life in the universe was quite slow. And then obviously since 3.7 billion years ago we've had this unbroken chain of like living stuff. There's been extinctions of stuff, but there's been this unbroken chain of life existing on Earth. So we've just been working on neurons, artificial neurons, for the last maybe 70 years or something, and life itself has been working on neurons for 3.7 billion years. So it's been a while since before we can catch up. It's gonna be a while before we can catch up. But anyways, back to our neurons. And I promise you the code for this thing is going to be very simple. What you really need to understand is how and why and where it comes from. And then once you understand that, you can build up on it. So entertain all the jumping around. The code is going to be maybe less than 20 lines. I think we'll build a neuron. I think most of it is here. We will build a neuron in less than 20. It sounds to me like it will be less than 20 lines. It will be one module as well. But as we go along and as we improve this, we're probably it's gonna grow into its own thing. Okay, so what does a neuron do? Yes, we want neurons. Yes, so this fires signals based on signals it gets. Okay, so if we simplify this all the way to binary logic, ones and zeros, we can say that a neuron or a perceptron is basically a function that gives a 1 or 0 output, a Boolean output. This is actually false because it should be a Boolean output. It gives you a Boolean output based on some binary inputs into it. Okay, so let's look here. Let's look somewhere here. Let us look somewhere. So we have binary input x1, x2, x3 into this, and then it becomes an output, one output. But the thing is, we have binary output, binary inputs. These binary inputs could be ones or zeros. Okay, cool. So it could be this or that. Cool, fine. But then the other thing that we need to do is, or rather that the inventor of this came up with, was weighting. Weighting as heaviness of the decision. So each input has a weight to it, and based on the sum of all the weights and the inputs, you compute some result. Okay, so you get weights, inputs, their weights, and some threshold that you need to cross, and then you compute whether the result will be a 1 or a 0. Let's make something intuitive here so that we can talk about it, easily. Let's make some sort of example, some easy example. You wanted to go to a restaurant. So my wife cannot eat gluten. Okay, so let's start with that. My wife cannot eat gluten, and I want to take my wife out to a restaurant. How will I choose a restaurant? Let's put two things. My wife really likes cheese, and my wife cannot eat gluten. Okay, so I'm gonna make let's make a neuron based on that. Let's try and compute that through a neuron. So my wife cannot eat gluten, and my wife really likes cheese. Okay, let's say because cannot is that's a very firm rule. So let's give that a weight of something like 2. Okay, and then let's say my wife really likes cheese. Let's give that a weight of something like 1. Okay, or let's give the the cannot cannot eat gluten a weight of something like 5, and then let's give like the weight of liking cheese something like 2, and then let's use a neuron to compute this. So my neuron is going to consider the 2 inputs. We're going to a place. Does it have cheese? Yes. So yes. So the weight of cheese is 2, and does it have cheese? The binary input of cheese is 1. Okay, cool. And then does all that cheese come with gluten? So if it's yes, the weight of that is gluten in it. The weight of that is something like, we say something like 5. So let's compute it. And then we say a threshold of crossing this is that it needs to be something like these are things that you will sit down and decide. But the threshold will be if there's cheese or not. Okay, if there's gluten or not, basically, because the weight of gluten is the most. Okay, so if there's gluten in the thing that my wife is going to be served, she cannot eat it, whether she likes it or not. Okay, so let's make it something like 4. So, and then we compute this. We compute this value, and we say there's a threshold of 4, and then we say 1, there's cheese, yes. 1 times the weight of cheese, 2, so that is 2. Plus 1, there's gluten, times the weight of gluten, 4. Okay. 5, we said. 1 times 5, it's 5. So 5 plus 2 is over the threshold of 4. Is it? Over the threshold of 4. So my wife cannot eat that. So the answer is 0. But if there was no gluten, the dish did not have gluten, so it was 1 plus 2. 1 times 2, weighted cheese, plus 0 times 6, weight of gluten, it becomes 2. 2 is under 4. If there is no gluten, my wife can eat that meal. I don't know if that makes any sense. But basically we are using inputs and their weights, and we're trying to compute an output compared to a threshold. Let me pause a bit and see if we have any questions. Do we have any questions? Okay, cool. So let's. The thing I'm going to do here is I'm going to let's actually start developing this completely from scratch. So we have a folder here, and this folder is on this. It's on this link, GitHub. GitHub Gaucho Rudy Gaucho repositories. Any questions so far? Rudimentary neural network. So it's nothing. It's completely empty. We're gonna just start it now. As you can see, I just made a README 5 minutes ago or 30 minutes ago. It seems like. So let's come in here and let's start by just start. Ooh, this is always a hard one. So Shift T, and then in there let's do some sane stuff. main.sh.c. Yeah, and then in here let's do ash include stdio h, okay, and then so int main takes nothing, and then I'll go in here and I'll do that, and then I'll say since we like writing matrices these days, int ret, and then here we should ret is equals to 0, and then let's do a return ret. rect. Okay, so let's do that. Let's run this for sanity purposes so that we know that this code actually works. Let's come in here and say print f. Let's say it here ret is equals 1, and then we shall do something like print this is the result of this is red. Let's put a new line there so we actually make the thing, make the buffer know the line is over and we can print. Excuse me. And then there's that. No. Yeah. And then we shall do that. Yeah, and then here we shall put in red, and then let's try and run this just so we know it is sane and it works. GCC main, and then out. Yeah, so we do get no, it puts a 0, so it returns a 0, so that's fine. I thought like, why is it not giving me an error? But I didn't I realized I added the 0 here. So let's implement some functions in here. So first of all, let's think about it. Each input has a binary value, and then each input has a binary value, and each input has a weight to it. Okay, so let's do that. Let's make a structure of a neuron input. So something like struct neuron input, and then in here we'll have int. This should probably be a boolean, but I'm not gonna do that because I don't want to boolean math. Int value, int weight, and then we should do that, and then I think we can do that, and that actually saves the thing, doesn't it? So if I went something like let's do input struct neuron, no, we can do neuron input equals, I think I can do something like dot value is equals 1, and I think I can do something like dot weight is equals 15. I can do something like that, and then I can do that, and then let's do our input. So ret input, this is our input. Let's say something like value, and then weight, and then we should put in here input dot weight, and then input dot input dot value, input dot weight. I think let's see, what's this? You're gonna say really, let's do structure. Okay. Okay, is that this probably looks like it's gonna break, but let's try that. Let's try and run this. Let us try and run this. feeling this is gonna break. 115. Why is it not breaking? Is it because we're not passing it by ref? Anyways, so git status, git add main C, git commit -m neurons, add neuron input. Okay, let's put that in. So we've made a neuron input. The way a neuron decides on, remember the thing. So fire sigmoid. Am I going to actually make a neuron? Does a neuron need struct? No, I'm not gonna make a neuron struct, but I might make a fire neuron, fire perceptron function. Let's make a fire perceptron function. I'm not gonna make a structure for neuron yet, because I don't need a function yet. Let's just go that. Let's just do that. And then let's say int fire perceptron. And then int fire perceptron will take in. Actually, I have it on the other side. But I think we'll do something like struct neuron input, and then this will be input, and then it'll go. It needs a threshold, int threshold to use, and then it needs size. We can even just start very size t, size input length, size int input length, int input length, and input length. Yeah, that's it. And then in here we'll do that, and we'll do that. Okay. No, this is actually just a function prototype because I just want it to be there. And then let's go that. So let's organically do this. I'm not gonna try and optimize before I need to optimize, so that I actually don't end up doing anything. So let's do that, and then let's do printf fire just to make sure it works, man. And then return 0. Okay, cool. I don't need to return anything, and we can always put we'll introduce instructs later. So here let's make two neuron inputs. So one neuron input of, let's call it cheese input, and then let's do that for the same thing, struct neuron input gluten input dot value equals 1, and then dot weight that is equals 5. Then we should do that. Let's finish that. Let's go in here. Let's make this cheese input something like 3. Okay. Think about it. Why do you have an error here? Okay. I'll remove this from here. X. I'll remove that. So let's do that, and then let's first of all make how do you make a list in C? I know this because I make this all the time. So I need to do neuron. Do I need? C list of structs. Yeah. Log list. Okay, cool. That's it. Neuron. Input. Yeah, I thought it would be that. Inputs equals dot, and then in here we'll do cheese input, and then we will do gluten input, and then we'll do that, and then we'll say that is that. Does this need that thing? Must use struct. It's fine. Okay. Yeah, let's see. This is a problem. That's where I'm lost. Okay, cool. So C is hard. Okay, cool. So that's fine. That's okay. Okay. So that will have choose input, gluten input, and then we can do something like fire. And then in here we can do something like and inputs. And then here we can do something like int threshold is something like 4. Let's leave it at that for now, and then we can put input length is 2. Okay, and then in here we go like, let's just confirm we're getting that for int I equals 0, I is less than input length, and then I plus plus, and then let's do that. Let's get in here, and then we can do print f. Let's do input values, input value equals to input st, and then what's the next thing? Wait, and then that is gonna d, and then in here we're gonna be like input I, and then I think something like that, value, and in here we'll do something like input I, and then in here we'll do something like wait, and then something like that, and then something like that, and then in here we want something like 10, and then in here we want something like it's already that. Okay. Let us see if that computes. Obviously, let us see if that computes. Let us see if that computes. So let's see if our fire neuron thing works. Okay, and then can we A out? Yes! Okay, cool. That's the first part we need to do. So the first part we need to do is that. The next part is we need to compute weighted sums. Compute weighted sums. I think I wanted a function, the compute weighted sums. Let's put compute weighted sums in its own place, because this function later becomes a function that we want to improve using SIMD, using assembly. So basically, if we separate it out now, because it's the function that has the matrix multiplication, we can simplify this quite a lot with matrix multiplication. So so the way I'd written this description is here, as I understood it. See here, we get a weighted sum from sum of weights, inputs, and length. So this function, this sum of weights, basically, if it's separated and if it's implemented in SIMD, this function becomes optimizable very quickly. Cool. So let's separate that out. Int sum of weights. So this will take int sum of weights. And then let's do this take struct neuron input input length. Ooh, okay. Let's go, and then let's implement int sum of weights. Yeah. Y, T, S, B. So in here, let's implement this sum of weights so that we return an integer. The way this works is we multiply each input. We make a sum, and into the sum we accumulate the value of we accumulate the value of the multiplication of the weight and the sum, and the weight and the value and the weight. That's how this works. So let's do sum int sum is equals 0. Okay, and then int and then here we want to return sum. Okay. And then before we do return sum, what do we want to do in here? What we want to do is we want to go for int I equals 0. I is less than input length. And then in here we want to do I plus plus. And in here we want to open that. And then in here we want to do sum is equal to sum plus inputs I times dot value times inputs I dot weight. There's a lot of error checking that needs to be done in this library, but we'll as we go along we will deal with that. And then after that it just returns the sum. Yeah, that's it. So we have a sum of weights. So basically what I want to do is fire perceptron. We have that. Int weight sum is equals sum of weights, and then in here we'll do this is inputs, and then in here we'll do input length, and then in here we'll do after that we'll do print f sum of weights is weight sum. So let's see, let us see sum of weights, weighted sums, sum weighted sum. Just because that there's that binary input that anyways, let's see if that runs. You see, man, one day this thing is not gonna cool. So I never did a printer here, and then I need to do this. And okay, cool. Okay. Input value 1, weight 3, input value 1, weight 5. Okay, cool. And what if we do something like input value here? Let's do 0, and then we see if actually this actually does work. This should be, you see, main out. The value sum of weight is 5. Perfect. So we can compute weighted sums. We know the sums of all the elements and the weight. So we know whether we're getting, if there's going to be cheese and the weight of cheese, if there's going to be gluten and the weight of gluten, and we have the sum of all of this. We can compute the sum of all of this. So if we go back to our description, of a perceptron, a function that takes several binary inputs and produces a single binary output. You know, if we have a fire perceptron and it takes weighted sums, and then based on these weighted sums, it just did the fire itself. You don't need a perceptron itself. You just need to give it a perceptron and a threshold. You need a function for firing. We don't need a structure for a perceptron. What we need to do is we need the function that fires we need the function that fires because we need to just give the perceptron, hey, this is the weight of the sums, this is the threshold you need to cross. Okay, so let's go look at some literature on how these weights work, and then we can come back. Do we have any more questions? Do you have any questions? No questions so far. So cool. Let's look at this neural networks. Yeah, some threshold value. So let's think about a threshold value so in our case it's a negation threshold value. So that makes it a little odd because it's a threshold value of which means don't. It's inverted. Because the thing that we care about the most is actually the thing that we don't want. We care about gluten the most, but we don't want gluten. So we sort of care about not wanting gluten the most. Okay. And how does this one, and how does the firing of this one work? So we need to set our weight so that when there's gluten, it's never, we will invert this later, I guess. Let us leave that. Let's leave that implementation detail to the applier to the person who consumes the library. Let's just deal with the library itself right now. So if there is gluten, we don't want to go. Okay, someone else will come and reverse it so that it goes like, if there's not gluten, we want to go. So if there's gluten, we don't want to go. So what threshold shall we set so that if it's crossed, we know that gluten is present? So if our total sum, if everything present is something like 8, and then if we just cheese present, it's 3. But anything more than 3 means gluten is present. So if we put a threshold of 3, it means if the weighted sums is more than 3, then we cannot go. Or rather, gluten is present and we don't want to go. So let's choose a threshold of 3. So let's choose a threshold of 3. So, and then let's make a fire perceptron. We have a fire perceptron neutron. So, no, it's in here that we're going to compute this. So weight of sums is that. And then we want to now, let's compute this return. Okay, this return. Is it a 1 or a 0? What weight are we passing into this? We're passing a weight of 3 into this. So right now we're passing a weight of 2. Let's pass a weight of 3. No. 2. Sorry. This is 2. Sorry. So that's the last part. So we're passing a weight of 4. That's fine. Let the threshold be 4. So that if ever there's gluten and the weight is above 4, we can't go. Because with gluten in, we will have 5, and that's above 4. Okay, so let's use a weight of 4. The one we... so here is... let's do this. So, if weight sum is greater than, if weight sum is greater than threshold, now here we need an int ret. This is okay. I'll just declare it here. Int ret. Okay, let's do that. And then in here we'll say something like ret is equals to 0. Don't fire. Or fire. That's fine. Okay. And then in here, else ret is 0. I think we just made the gluten neuron actually. Doesn't matter. So that's cool. So and then here we will return ret. Okay. Okay, cool. So we will return ret. So this tells us whether to fire the perceptron. Okay, and then here int fire is equals here. if int if fire is less than 1, what does that mean? There is no gluten, yes? Yeah. If fire is less than 1, we already got to the consumer of the API. We thought we were pushing this problem around. So let's go print f. There is no gluten. We can go. And then let's put a new line there. New line. And then else print f there is gluten. There is gluten. We can't go. N. Oh, that was gonna bite me just now. And then let's do this. Let's boom. Print f. Okay. Okay, cool. Okay, cool. So let's do this. So is there any way we print weighted sum? And then print f the threshold here as well. Threshold is and I'm going to put in two new lines so that we can see the results in its own thing and the threshold. Right. Okay, and then that. Okay, so let's do this. Let's check this if this actually works. We should probably make this a CLI application so that we can feed in parameters from CLI. But hey, we started this from scratch on this stream, so that's it. We're gonna build this. So let's fire that. Threshold is 4. There is gluten. We can't go. Sum of weight. Wow, it worked. Look. Input value 1, weight 5, gluten. We can't go. Okay? So in here we can go something like my word. So let's where are we firing this stuff? Unfortunately we don't know the type right now, so it's fine. But let's do something else. Let's put cheese in. And let's now allow for cheese and gluten. Let's see. This is the main. Let's see. Threshold is 4. We can't go. There is gluten. We can't go. Okay, cool. Let's look at the next one. Let's remove the gluten. Perhaps we don't have gluten here. What happens? Okay, cool. Let's compute that. Just see main. Let's do that. Boom. Sum of weight. There is no gluten. We can go. Look at that. We just implemented a very simplistic neuron, a perceptron neuron. Based on based on the input we give it and the weighted inputs we give it, it can decide whether we go to a restaurant or not. And it will choose this based on cheese and weight, cheese and gluten. Okay, so if you've done any sort of algebra or any sort of pre-calculus or calculus, you do realize that this function of ours, what we're basically producing is a step function. And a step function is something that just jumps. Step function. A step function. Step function. A step function goes from like 0 to on. It's here, but it's hard to show this. Yes, here. This is a step function. It goes from 0 to on, or it goes from on to off, or 1 to off, or whatever way I wanted to, whatever way I can describe that. Basically, the threshold is very tight. Okay, it has a sort of brick wall threshold, and over this threshold you just go to the other side. But in reality, in the real world, things are not so that defined, because even in this situation, the reality isn't that my wife can't have gluten. Is that some certain types of gluten is what my wife can't have, and even at that point, it's some amount of those types of gluten. So really what we want is not a function that goes on or off. Really we want a relative function that kind of sort of climbs this ladder slowly, and then it takes account for all the real worldness. And what I basically described is something that happens in nature all the time. It's basically a Gaussian distribution. And a Gaussian distribution is called a normal distribution, where it's a bell curve, okay? It's a bell curve. There's a on ramp, there's a gradual on ramp, and then there's a gradual off ramp. We don't want a discrete on ramp and a discrete off ramp. And the way to calculate this is by using a different type of neuron. And the different type of neuron that we're going to use is called a sigmoid neuron. The reason it's called a sigmoid neuron is because of the sigmoid function. And the sigmoid function is basically a function that can squeeze a number between negative infinity and positive infinity. Someone's gonna be like, look at that guy, he doesn't know math. It can squeeze very small numbers and very large numbers into a representation of between 0 and 1. You see? So we still get the discrete thing we want. We still get the discreteness. The decision will still be a 0 or a 1. But the way the sum is done is more gradual, is more accepting. And what this does is it allows us to account for the continuous nature of the real world. Okay, the real world isn't like some on or off thing. There's volumes to stuff. You can add the volume, you can increase the volume or reduce the volume. Okay, so in this way, the sigmoid curve enables us to do that. So the next kind of neuron that we need to implement is a sigmoid neuron. And the way a sigmoid neuron is, it uses the sigmoid plotting function, and uses that to how do you say this? It uses the sigmoid plotting function to climb some sort of some Cartesian plane, okay, or go down the Cartesian plane, okay. And this is very easy. And I think since my time is up for today, I usually do a 1 hour stream. I'm going to leave this as a challenge. And there already is a formula on my write-up here, which explains on how to implement. Basically, once we have the sigmoid neuron, we can return. Once we have this weighted sums, once we have a weighted sum, we can return. We can fire the sigmoid neuron using this formula, using an exponential formula. Okay, so but this is easy enough to do. I can do this in one line. Okay, the real part, the hard part is to go and understand why do you need to use an exponential, and how does a sigmoid neuron kind of relate to this, so that you can do this. And if you have some time, since we have this library out there, I would challenge anyone, the first person, to write a pull request that adds a fire sigmoid function into the code. This should be easy. It's a one-liner, I think. Let me push this up. Git push. So that it's up there. So the code is on now. So the code is online now. Whoever wants can use the this. Let me do that. The rules. So let's add some rules. If you want, you can add a pull request to this thing that allows you, that enables firing of a sigmoid neuron. Yeah, let's leave that for today there. Unless someone has any questions, that should be cool. That was routinely amazing. I think tomorrow we might consider implementing a small neural network, depending on how much reading I manage to do today. Tomorrow we might consider implementing a small neural network and see how we can kind of build those up. Okay, that's amazing. Thank you so much for coming today. Thank you, Abhishek, for the question. I'll check out on why we're using sigmoid neurons instead of if ReLU is more stable, and we'll cover that in the next stream. Thank you so much for coming. That has been a fun learning session and a fun building session, and this is us building our git status git diff dash staged. Okay, git commit dash m neurons implement perceptron fire. Okay, git push. Okay, cool. This has been amazing. So thank you so much. That's the beginning of that is the beginning of a neural network library that we're going to build up slowly and perhaps, if even possible, use in our own application. Remember, the point of this isn't to build the best and the greatest, is to build our intuitions of how these things work by actually doing them in practice. You can also choose to go and read 1,000 books on this. It's not, whichever you choose is based upon you. That's not a problem. But we are just building our intuition by taking one thing and building it up and building it time and time over again. Thank you so much for coming to the stream today. Check you next time. See you tomorrow. And that was an amazing one. Cheers.